Hi, this is Ken Willis of Cadence Design Systems. Welcome to Sigrity Tech Tips. Today we bring you another installment of how to sign off your designs using a power-aware signal integrity methodology. Our video today will show you how to resolve basic signal integrity concerns before your PCB is even routed. Using this methodology, you can avoid wasting hours of rerouting a PCB late in the design cycle and having to re-verify signal integrity. Using the Allegro interconnect flow planning technology, issues such as improper route topology, missing termination, overshoot, ring back, and extended settling delays can be quickly identified and resolved. Since the pre-route analysis uses transmission line lengths based on the Allegro component placement and the proposed bus routing topologies, realistic simulations can be run very quickly at this stage before routing of the PCB even gets started. This approach is an important step in a power-aware signal integrity methodology. By addressing basic reflection-related SI issues early in the design cycle, signal integrity experts are freed up to focus on the difficult crosstalk, timing, and simultaneous switching noise problems as PCB routing tasks progress. By taking this whole category of problems off the table up front, the more complex SI problems can be given proper focus, and you can be more confident that you can sign off on your design on a predictable schedule, and that will keep your boss happy. In today's video, you will see us utilize the Allegro Sigrity SI Base. To learn more about this product, visit us at www.cadence.com. Now I'll turn it over to my colleague, Dennis Nagel.
Allegro Sigrity SI can be used at any stage of your design flow, and in fact can be used earlier and in ways that you may not have previously considered. It is a fully capable SI environment blending Allegro and Sigrity technology. Today we'll be looking at analyzing a PCB, but it works equally as well with package designs. Allegro Sigrity SI can be an integral part of any constraint-driven design flow by enabling SI analysis at both the design and topology level, as well as providing editing and screening capabilities. We all know that a constraint-driven flow saves time and prevents issues from propagating down to SI sign-off. Historically, that flow included pre-layout analysis, which can start at any time and help define your solution space and corresponding electrical constraints. But what about post-layout? There's an obvious goal of reducing the overall effort required for sign-off, but with today's design trends, can you trust your constraint process to catch everything? Should you be waiting until the design is completely routed to start your analysis? Let's take a look at what we typically concern ourselves with in the SI domain. We have signal quality with things like overshoot and ringback, timing-related issues like delay, what kind of topology works best for the situation and whether or not termination is needed, and of course crosstalk. Now ask yourself if you need interconnect to investigate all of these. Naturally, the one that absolutely requires router traces in place is crosstalk. If we're going to be talking about unrouted designs in Allegro Sigrity SI, then we also need to discuss flow planning. If you open an unrouted design, you are typically faced with aptly named rat's nest lines that provide a simple indication of each pin pair that is not fully connected with etch. From an SI perspective, we typically represent each pin pair distance at this stage with a Manhattan length. And while adequate in most instances, it's still just an estimate. It's unrealistic to expect that each connection will be routed in a straight line, when in reality it will be much closer to a sum of the X and Y distance. Flow planning was recently added to Allegro Sigrity SI, where it allows you to graphically define and capture design intent. This design intent makes sense for major interfaces, but also can be applied to any logic in the design. Here's the same design with flow planning applied. So this makes perfect sense in terms of driving the router, but what if your pre-route SI analysis could leverage the same data? What if the length of your unrouted connections were based on the length of the flow planning guidance? Would this allow you to better optimize your design? Here's the design we'll be looking at today, which is currently in an unrouted state. The difference in rat's nest appearance is Allegro's ability to color rats based on layer transitions or whether the pins of a particular connection are all located on the same layer, like top for example. Everything might look like it's not too complicated at the moment, but let's open a view where we're just looking at the address bus for the memory interface at the top. It's a little bit messy and certainly not going to work for our desired flyby topology. Flow planning creates rat bundles, which are essentially a grouping of rat's nest lines at the pin pair level. Because of this, you may need to schedule some of your nets that contain multiple pins. There is no fixed order to this. You can schedule first and then create your rats bundles, Or you can create your bundles first, and in some cases, it will then be obvious that a topology schedule is needed. In order to fix the current scheduling problem, we will apply some electrical constraint sets in Constraint Manager. As we do this, we can see that the correct flyby topology is generated. We have a different topology for each bank. We do this in order to get the correct scheduling and constraints created. Let's fast forward a little bit and take a look at the design after flow planning is finished. This certainly gives a better sense of how all the major routing will take place. The appearance of the bundles are different based on several factors. Coloring can indicate a default bundle, or one where the etch is limited to a specific layer. In other cases, a bundle with a crosshatch or dashed appearance was auto-generated based on net groups in the design, whereas solid-colored bundles were generated manually. If we revisit the memory interface at the top, we can see a much cleaner view of the entire interface. Here are the bundles comprising the address buses for the two banks. Also notice we've decided to have the data route on the outside of the memory chips and leave the inside for address and control. The question now is this going to work? Well, we don't have to wait until everything is routed to find out. In the analysis preferences, the default settings for unrouted interconnect is shown. We can set a default impedance and notice that the default for % Manhattan is 100. If we wanted to take into account the difference in length for various nets without flow planning, it would be a tedious process to go alter the % Manhattan setting over and over for various groups of signals. This is no longer necessary now that flow planning is taken into account. If we run a simulation for the DQ nets in this interface, we can easily run all the nets in both directions and in very little time. This can generate reports and or waveforms. Let's take a look at all of the waveforms from the controller to the chips. We have both banks, and within each bank, any difference in delay is a result of the more accurate length in each flow plan. This length is a combination of the flowed bundle plus the individual rake lines for the connection at each end. If we make the etch visible on just the non-plane layers, we can see that the only etch is some power and ground shapes. Looking at this bundle here, this contains a group of signals that it should avoid the power shapes and the memory interface on the left. Let's see what the Manhattan lengths of these signals already are. They are already close to 10 inches. If we decide to flow plan this bundle to drive the router, we can do so by simply selecting the flow and clicking to add or move vertices. Or we can use a new command to guide the flow all at once. With a couple of clicks, which is very analogous to the way you would actually add etch, we can start to drive the design intent for routing and avoid the areas that we want to. And just like that, we've controlled how this bundle will be routed. Let's look at the result of what we did. If I extract one of the nets of the bundle to Signal Explorer, we will see a single T-line model representing the net. We've increased the length by more than 3 inches. Is this okay? We can go back and simulate in the design, or we can just as easily simulate here. Now would be a good time to see if we need a stronger driver to handle the length and loading. Even worse would be if this problem was not evident with the original 10-inch Manhattan distance. In this demo, you've seen just a few of the features found in Allegro Sigrity SI. We've seen that pre-route and pre-layout are in fact different types of analysis, and that pre-route can be used to detect SI problems earlier in the design cycle. Pre-route is the best time to find out if you need any terminators, as they are too painful to add post-route. And finally, we've seen that because flow planning drives design intent in terms of how the routing will take place, it can be useful at the pre-route stage to improve the accuracy of SI analysis. Flow planning can also lead you to placement edits or changes, which are also painful after investing any time in routing.
Thank you for watching another edition of Sigrity Tech Tips. For information on products used in today's video, click on the links below or contact your local Cadence sales representative or Cadence channel partner.